All right, so this is day 2 of notes number 19. So we're talking about exponential functions. And we're going to use a calculator for this portion of the notes because we're starting to talk about some applications and the natural base e. So there are a lot of applications where a good number for a base number is the irrational number e. E is an irrational number like pi. We all know that pi is 3.14159, etc. E is similar. It's a common ratio found in lots of relationships in nature and finance and exponential growth. And so we use this number a lot. So you should know that E is about 2.718. Beyond that, I don't really pay much attention. F of x equals e to the x is the natural exponential function because it's got the natural number as its base. So sketch this graph. We already talked about graphing exponentials before. Remember, we said every exponential graph has a nice, easy number of when you plug in 0, any number to the 0 power is 1. So we still have 0, 1. When you plug in 1, you get the base number. So remember, you need to know E is about, basically you need to know E is about 2.7 if you're just sketching a graph. Plot that in. And we still have a horizontal asymptote of y equals 0, because if you have a positive base number raised to an exponent, there's no way it will ever equal 0. It can get very close, but it won't equal 0. As we start plugging in large negative numbers, this becomes 1 over e to the 1 millionth, for example, but it doesn't get to 0. So I'm not sure where my other point went. So I'm just going to sketch a graph kind of like that. And if I have e to the negative x, remember this is a y-axis reflection because e to the negative x is like having a negative inside of your function. So instead of the 0.01, well, no, I still have the 0.01, excuse me, but instead of the 0.1, 2.7, I've got negative 1 and e, which is about 2.7. You would still have a horizontal asymptote at y equals 0. So negative 1, 2.7, 0, 1. This graph would decrease, approaching 0, but not actually reaching 0. All right, so what about the applications? Two really common applications are the compound interest problems, and we have two formulas. One is when the interest is accumulated a certain number of times per year. So we use this A, which is, let's label things out here. So A is the account balance, like how much is sitting in the account after a certain amount of time. P is the principal amount. That's just like the initial amount. How much did you put into an account to start with? The 1 is built in. R is the interest rate, annual interest rate, as a decimal. So if you have 5% interest, you're putting it in as 0.05. N is the number of compoundings. Compoundings is how often are they taking a percent of what's in the account and adding that as interest. So is it once a year? Is it twice a year? Is it every month? 4 times a year? That'll be told in the problem. And then finally, there's a T in there. T is the time. It has to be measured in years. So if it's given to you in months, you need to change that to a decimal of a year, a fraction of a year. Now, sometimes instead of saying interest is collected a certain number of times per year, sometimes interest is collected continuously. So there is no n value. N would be infinity, right? So as n approaches infinity, by the way, this base number becomes e to the rt instead of 1 plus r over n to the nt. So this is for continuous compounding, or in other words, interest is always being collected in the account every second of every day. We can't put an end to that. Everything is the same. A is the account balance, P is the principal, R is the interest rate as a decimal. T is the time in years. Base number E is about 2.718, dot, dot, dot. We have an E. We can just type in E in Desmos and it will know what number that is. Solve each problem. So a total of 9,000 is invested, that's P, at an annual interest rate of 2.5%. So R is 0.025. Remember, you just divided by 100 for 5 years. That's T. Find the balance after 5 years if the interest is compounded semi-annually. So how many times a year is semi-annually? That's twice. Semi means cutting in half. Quarterly will be n equals 4. Daily, we're not assuming leap years or anything, so n equals 365 days in a year. Continuously, we use our PERT formula. All right, so I'm going to write these formulas out to start, and then I'm going to just make adjustments in Desmos. So A is 9,000 times 1 plus R over N, so 0.025 over 2, to the NT. That's the most common mistake because this one's to the RT, this one's to the NT. So 2 times 5. This equation is going to be A equals 9,000 times 1 plus 0.025 over 4 to the 4 times 5. This one is going to be A equals 9,000 times 1 plus 0.025 divided by 365 to the 365 times 5. The last one I'll do in a second, but these three, in Desmos, I will only have to adjust the 2 places where n changes. So let me switch over to Desmos here. I'm going to split screen. All right, so you don't need to type in the A equals part. We're just calculating a number, so we're not trying to graph anything. It's just going to be 9,000 times parentheses 1 plus 0.025 divided by 2 to start. Raise that to the 2 times 5 power. So let's write this number down. Now we're talking about money, so even though we normally round to 3 decimal places, let's put a $sign on this and say the account balance is 10,190 round to the nearest cent, 0.44. Okay, my next one is going to be the same thing. I'm just going to switch out, change this 2 to a 4, and change this 2 to a 4. That was easy. Okay, so, and you can see the answer adjusted as I did that. Again, put a $sign in there, 10,194.37. It makes sense that if we collect interest 4 times a year instead of 2 times a year, we should have a slightly higher amount in our account because you're taking a percentage of what's in the account each time. So you get to do that more often if it's quarterly. Daily should be our highest out of the 3, right? And we can just change this 4 to 365. And again, all of our numbers are pretty close. None of those changes made a difference of like thousands of dollars or anything. So if you had a typo somewhere or if you forgot to change an answer, that hopefully you catch that as you're looking at your answers. But that's my daily. All right, and then continuously. Remember, you're using a different formula for continuously. So continuously, it's A equals 9,000 times E to the RT, 0.025 times 5. So now let's type that in. 9,000 times E. See how it recognizes E as a number? To the 0.025 times 5. Oops. I need that times 5 to be up in, it really doesn't like that. I kept trying to hit times 5 and it wasn't letting me stay in the exponent. So I'm going to say times 5 like this. Again, this should be very close to daily. It should be slightly higher because compounding continuously is more than just once a day. So this is 10,198.34. So just about 5 cents more, but still. That should always be the case. You'll get a slightly higher number with continuously than daily. All right, so compound interest formulas, make sure that you have those two memorized. All right, what else could we do with these formulas? So this one says let Y represent the mass in grams of radioactive strontium. Here's this little symbol on the periodic table, I think, whose half-life is about 29 years. So what does half-life mean? It means it takes, so say you start with 10 grams. I think that's what we're starting with here. You start with 10 grams. It takes 29 years for that radioactive strontium to just sit there and start deteriorating down to 5 grams. It'll take 29 years for that to happen. It would take another 29 years for it to get down to 0, if it ever actually can get to 0. The quantity of strontium present after T years is this. Y equals 10 times 1/2, because of half-life, to the T over 29. Let's talk about this formula. Again, half-life represents how long will it take you to get half of what you had. So this formula makes sense because if you plug in 29, you get 10 times 1/2 to the first power. So you get 5 grams. So whatever T you're plugging in, it compares it to the half-life, and that's sort of what ratio, that you would have left over. What characteristic of the equation makes this a decreasing function or exponential decay? It should look something like this, right? Oh, not dipping below, though. It should look like a decreasing function. Why is that? It's the fact that the base number is a fraction between 0 and 1. If that were 2 to a power, it would be growing, right? So the base number is between 0 and 1. What is the initial mass? Initial is always when time equals 0. So evaluate Y of 0. I don't need a calculator for that because any number that's not 0 to the 0 power is equal to 1. So 10 grams to start. How much of the initial mass is present after 80 years? So we should just be plugging 80 in. I already know it should be less than 5 grams because it only takes 29 years to get 5. So 10 times 1/2 to the 80 divided by 29. We're going to round this to 3 decimal places. Since we're not talking about dollars and cents anymore. So 10 times 1/2 raised to the 80 over 29 power. Rounded to 3 places, this is 1.478. Always label your answer. This was measured in grams in the problem, so this is how many grams are left. About how many years will it take for 0.3 grams to remain present? So this is not asking us about finding an amount. We're trying to figure out the time. So if I set this equation equal to 0.3, I want to solve for t. Now, we haven't talked about solving log equations yet, so we need to, even if you remember how to solve by log equations, solve by graphing. If you're going to use a graphing calculator, if you're allowed to, it is so much easier to solve by graphing, and then you don't have to make any computational errors. So how do we solve by graphing again? We say y equals, graph the function, y equals 10 times 1/2 to the, I don't want to use t. I want to use, I could use t, but I would need to make this like f of t. Let's do that. Either use f of t or change that to like x. So t over 29. I don't think it'll let you do y of t. Let's see. Oh, yeah, well, okay. Y of t equals 10 times 1/2 to the t over 29. And what are we trying to do? When does it equal y equals 0.3? Now, we might have to do some zooming out, right? We know that we got down, took us to 80. 80 years took us down to 1.473. So it's got to be something past 80. And how do I know where these cross? It's a little bit of guess and check at this point. If I click near, see this general region where it was like, I see red. No, I don't see red. I clicked in the general region and a gray point popped up. There it is. So the answer is how many years? 146.708. I will show you in a bit later in this chapter how to solve this algebraically. But if we're allowed to use a calculator, it makes sense just to graph and find the intersection, no matter what our functions are. All right, that finishes our second day of notes, and we're just going to practice some of these applications and practice them with Desmos.